Good evening and welcome to Dreamy Academy. Tonight, we begin a quiet journey into a world that is both utterly familiar and profoundly mysterious, the world of water. As we begin, I'd love to know where you're watching from, your city, your country, perhaps even what the night sky looks like outside your window. If you enjoy these peaceful explorations of science, please take a moment to like the video and subscribe. It truly helps this little corner of quiet curiosity grow. To those already subscribed, thank you sincerely for being part of this slow and thoughtful adventure. Consider for a moment the water that flows through your very being. Over half of your body right now is water. It carries nutrients, regulates your temperature, and allows the intricate dance of life to unfold within every cell. It is the silent, constant medium of your existence. And yet this seemingly simple substance, 2 hydrogen atoms, 1 oxygen, holds secrets that defy expectation, principles that shape planets, and a history that stretches back to the earliest moments of our cosmos. Hydrology, the study of water, isn't just about rivers and rain. It's about the fundamental nature of existence, the delicate balance that allows life to flourish, and the patient, endless work of a planet shaping itself. It is a story of beautiful paradoxes, of hidden forces, and of a molecule so perfectly suited for its role that it seems almost designed for life itself. To contemplate water is to contemplate the very essence of Earth, and indeed, the universe. It is a subject that rewards patience, that invites us to slow down and truly see the wonder in the ordinary, the profound in the commonplace. So let us begin our quiet drift into the heart of water. Have you ever truly considered, the quiet miracle of a single drop of water? It flows, it dissolves, it sustains. It is the backdrop to every living moment on Earth, yet its properties are so peculiar, so specific, that they hint at a deeper, more profound story. To understand the vast oceans, the towering clouds, and the life-giving rivers, we must first shrink our gaze, not to a raindrop, but to the very essence of water itself, the single, unassuming molecule of H2O. Let's begin by imagining this tiny entity. At its heart lies an oxygen atom, a relatively robust presence with 8 protons in its nucleus. Around it, like whispers, orbit its electrons, yearning for stability. Into this atomic sphere drift 2 hydrogen atoms, each a single proton with a lone electron. They are the simplest of elements, yet together they form a partnership of profound consequence. In the water molecule, these atoms don't just sit side by side, they bond. The hydrogen atoms share their single electrons with the oxygen, and the oxygen in turn shares electrons with each hydrogen. These are called covalent bonds, a gentle agreement of shared electrons that holds the molecule together. But here's where the story begins to twist in fascinating ways. If you were to picture the water molecule, you might intuitively imagine it as a straight line, like beads on a string, H-O-H. Yet this isn't its shape at all. Instead, the water molecule is elegantly bent. The 2 hydrogen atoms angle away from each other, forming a V-shape, with the oxygen at the vertex. The angle between the hydrogen atoms is about 104.5 degrees, a precise geometry that is crucial to everything that follows. This bent shape isn't arbitrary. It arises from the subtle dance of electrons. The oxygen atom, being larger and more attractive to electrons, pulls the shared electrons in the covalent bonds a little closer to itself, away from the hydrogen atoms. This creates an uneven distribution of charge across the molecule. The oxygen end, having a slight excess of electron density, develops a subtle negative charge. Conversely, the hydrogen ends, having had their electrons drawn away, become slightly positive. We call this phenomenon polarity, and it transforms the water molecule into a tiny electrical dipole, a miniature magnet with a positive end and a negative end. This polarity is the invisible thread that weaves together all of water's astonishing properties. Now imagine billions upon billions of these tiny polarized magnets floating in close proximity. What happens? They attract each other. The slightly positive hydrogen end of one water molecule is drawn to the slightly negative oxygen end of another. This attraction isn't as strong as the covalent bonds within a molecule, but it's powerful enough to create a network of fleeting yet pervasive connections. These are called hydrogen bonds. They are the gentle, invisible glue that makes water. Well, water. It is these hydrogen bonds that give water its remarkable stickiness. This stickiness manifests in several beautiful ways. Firstly, there's cohesion, the tendency of water molecules to cling to each other. This is what allows a drop of water to hold its spherical shape, or why a water strider can glide across the surface of a pond without sinking. This surface tension, a delicate skin of hydrogen-bonded molecules, supports its weight. Secondly, there's adhesion, the ability of water molecules to stick to other surfaces. This is evident when water climbs up a narrow tube against gravity, a phenomenon known as capillary action. It's how a paper towel soaks up a spill, and more profoundly, how trees can draw water from their roots up to their highest leaves, defying the pull of the earth. Perhaps one of water's most celebrated qualities is its role as the universal solvent. Because of its polarity, water can effectively surround and pull apart other charged molecules, like salts. The positive ends of water molecules are drawn to the negative ions of a salt, while the negative ends are drawn to the positive ions, gently prying them apart until they dissolve. This dissolving power is utterly essential for life. It allows nutrients to be transported within organisms and enables the countless biochemical reactions that define living processes. But the true marvel, the beautiful paradox that underpins life on Earth, lies in how water behaves when it freezes. Most substances become denser as they cool, with their solid form being heavier than their liquid. Water, however, is different. As liquid water cools, its molecules move slower, and the hydrogen bonds become more stable, locking the molecules into a more ordered, hexagonal lattice. This lattice, surprisingly, is less dense than liquid water because the molecules are held slightly further apart than they are in their more chaotic liquid state. This is why ice floats. Imagine a world where ice sank to the bottom of lakes and oceans. During winter, entire bodies of water would freeze solid from the bottom up, trapping and killing aquatic life. But because ice floats, it forms an insulating layer on the surface, protecting the life beneath and allowing it to survive even the harshest cold. This single, peculiar property of water is a cornerstone of Earth's climate and the very existence of complex life. So, we've seen how the humble architecture of a single water molecule, with its bent shape and resulting polarity, gives rise to a cascade of unique properties, its stickiness, its solvent power, and its life-saving ability to float as a solid. These aren't mere curiosities. They are the fundamental principles that govern the distribution and behavior of water across our planet, making Earth the vibrant living world we know. This elegant dance of atoms, this cosmic architecture, is not an accident. It is a story woven into the fabric of the universe itself. But where did this extraordinary molecule come from? How did such a precious substance, forged in the hearts of ancient stars, arrive on our young planet in such abundance? And how did it shape the Earth into the watery world we inhabit today? That question leads us from the microscopic elegance of the molecule to the vast planetary scale of its presence, as we begin to explore the great reservoirs of water that define our blue marble. Welcome back, curious minds, to Dreamy Academy. In our last gathering, we peered into the very soul of water, dissecting its elegant molecular architecture and marvelling at the hydrogen bonds that gift it such extraordinary properties. We understood what water is at its most fundamental and how it behaves on a microscopic scale. But we left a few profound questions lingering in the cosmic silence, didn't we? We asked, from where did this mysterious, life-giving substance truly originate? How did it arrive on our young planet in such astonishing abundance? And what role did it play in shaping the very world we inhabit, long before life, as we know it, could even dream of stirring? Today, we embark on a journey that stretches across billions of years and unimaginable distances, tracing water's epic saga from the birth of the universe to the vibrant blue marble we call home. To understand water's origin, we must first cast our gaze far beyond Earth, to the very beginning of everything. Have you ever considered that the hydrogen atoms within every single water molecule on Earth are, in essence, as old as time itself? They are the universe's primordial building blocks, forged in the fiery crucible of the Big Bang mere moments after creation. These are the simplest, lightest atoms, the fundamental breath of existence. But hydrogen alone does not make water. For that, we need oxygen. And oxygen, unlike hydrogen, is a product of stellar alchemy, born in the hearts of giant stars. Imagine, if you will, colossal celestial furnaces, burning bright for millions of years, fusing lighter elements into heavier ones through processes we call stellar nucleosynthesis. When these magnificent stars finally exhaust their fuel, they often explode in spectacular supernova, scattering their newly forged elements, including oxygen, across the vast expanse of interstellar space. So, we have hydrogen, ancient and ubiquitous. We have oxygen, born of dying stars, now adrift in the cosmic dust. What happens next? These atoms, along with countless others, begin to coalesce within vast, cold, dark interstellar clouds, often called molecular clouds. These are the universe's nurseries, where new stars and planets are destined to be born. Within these swirling nebulae, hydrogen and oxygen atoms find each other. Sometimes they meet by chance collision. More often, they are drawn together on the surfaces of tiny icy dust grains, microscopic cosmic catalysts, providing the perfect conditions for these two elements to bond. It is here, in the cold, dark embrace of these cosmic nurseries, that the first H2O molecules are formed. Billions of them, trillions. They are born in the silence of space, tiny bent V-shapes, each carrying the blueprint for life, long before any planet could even fathom their existence. They drift, frozen onto dust grains, waiting. Now let us bring our focus closer, to our own solar system, some 4.5 billion years ago. Our Earth, in its infancy, was a very different place. Freshly accreted from the swirling protoplanetary disk, it was a molten, fiery sphere, constantly bombarded by debris. Any water present during its initial formation would have quickly boiled away into space. So how did our planet become the water world it is today? This is where the story truly becomes epic, involving a cosmic delivery service of truly monumental proportions. For a long time, scientists debated the primary source of Earth's water. Was it outgassed from the planet's interior through volcanic activity, slowly accumulating over eons, or did it arrive from space? The evidence increasingly points to a celestial origin, primarily through the impact of comets and asteroids during a period often referred to as the Late Heavy Bombardment, roughly 4 to 3.8 billion years ago. Imagine the early solar system, a chaotic cosmic shooting gallery. Beyond the snowline, a region in the protoplanetary disk where temperatures were cold enough for volatile compounds like water to condense into ice. Countless icy comets and water-rich asteroids formed. These celestial wanderers, some as large as small moons, were essentially frozen time capsules carrying vast quantities of the H2O molecules that had formed in the colder reaches of space. Gravitational perturbations from the gas giants, particularly Jupiter and Saturn, are thought to have flung many of these icy bodies inward, sending them on a collision course with the inner planets, including Earth. For hundreds of millions of years, our planet was relentlessly bombarded by these celestial messengers. Each impact was a violent event, but each also delivered a precious cargo, water. As these icy comets and water-rich asteroids disintegrated upon impact, their frozen H2O would have vaporized, forming a dense, steamy atmosphere around the nascent Earth. As the planet slowly cooled, this water vapor condensed, falling as torrential rains that lasted for millennia, gradually filling the deepest basins and forming our primordial oceans. How do we know this? The answer lies in a subtle, yet profound chemical fingerprint, the deuterium to hydrogen D/H ratio. Deuterium is an isotope of hydrogen, meaning it has an extra neutron in its nucleus, making it slightly heavier. The ratio of deuterium to ordinary hydrogen in Earth's oceans is a unique signature. By comparing this ratio to that found in various cosmic bodies, scientists can trace the likely origin of our water. Studies of certain carbonaceous chondrite meteorites, a type of asteroid, and some comets have revealed DH ratios strikingly similar to Earth's oceans, strongly supporting the theory of extraterrestrial delivery. While volcanic outgassing undoubtedly contributed some water vapor from the Earth's mantle, the sheer volume of water points overwhelmingly to these cosmic ice bearers. With its arrival, water began its tireless work, transforming a barren, rocky world into a dynamic, living planet. The continuous downpour accumulating in the low-lying areas gave birth to the first oceans. These weren't the serene blue expanses we know today. They were likely warmer, more acidic, teeming with dissolved minerals from the fresh volcanic rock. And almost immediately, the hydrological cycle in its most nascent form began to stir. The sun, though fainter than it is now, still provided enough energy to evaporate water from the surface of the young oceans. This water vapor rose, condensed into clouds, and fell back as rain, initiating the perpetual dance that continues to shape our planet to this very day. Water, the universal solvent, began its relentless task of erosion. It carved channels into the fresh volcanic landscapes, carrying dissolved minerals and sediments from the land into the newly formed seas. It began to sculpt the continents, albeit in embryonic form. This process of weathering and erosion driven by water not only reshaped the planet's surface but also played a crucial role in cycling nutrients and elements, preparing the stage for the greatest act of all, the emergence of life. Indeed, many scientific theories regarding the origin of life on Earth place water at the very heart of the process. Whether in a quote 6 warmed by the sun, or within the mineral-rich, chemically active environments of deep-sea hydrothermal vents, water provided the medium, the solvent, and the transport mechanism for the complex chemical reactions that eventually led to the first self-replicating molecules. It was the cradle of life, the amniotic fluid of our planet. Consider the profound paradox. Water, born of cosmic violence and stellar death, delivered to Earth by destructive impacts, ultimately became the gentle, nurturing force that allowed life to flourish. It transformed Earth from a desolate rock into a vibrant, blue oasis, a truly unique jewel in our solar system, perhaps even in the galaxy. Without this cosmic journey, without the specific conditions that allowed for its formation and delivery, our planet would be a very different place, devoid of the intricate dance of life that defines it. As we look out at the vastness of Earth's oceans, at the intricate network of rivers, at the clouds drifting overhead, we are not just seeing water, we are witnessing the culmination of a 4.5 billion-year-old journey. We are seeing hydrogen forged in the Big Bang, oxygen born in the hearts of ancient stars, molecules formed in cold cosmic dust and delivered to our world by icy wanderers. This is the story of water, the architect of our planet, the silent, tireless force that continues to move, to sculpt, and to sustain. In the chapters to come, we will dive deeper into this continuous movement, exploring the intricate details of the hydrological cycle, understanding how water interacts with the atmosphere, the land, and even within the very bodies of living organisms. But for now, let us pause and reflect on this epic journey, marveling at the cosmic origins of the seemingly simple substance that makes our world truly unique. What wonders, we ask, does this ceaseless cycle hold next? Subscribe to Dreamy Academy to continue this incredible journey with us. Having journeyed across the cosmos, from the heart of a dying star to the frosty embrace of an interstellar cloud, and then endured the fiery crucible of Earth's early formation, water finally found its home. It condensed, it gathered, it began to sculpt our nascent planet, giving rise to the very oceans we now gaze upon. But its work, its endless dance was far from over. Indeed, it had only just begun. Now, we turn our attention to the magnificent ceaseless ballet that defines water's existence on Earth, the hydrological cycle, or as it is more commonly known, the water cycle. Imagine a grand, invisible circulatory system, perpetually in motion, breathing life into every corner of our world. This isn't merely a scientific diagram, it is the very pulse of Earth, an intricate, dynamic interplay of energy and matter that ensures water, in all its forms, is forever on the move. It is a testament to water's paradoxical nature, constantly changing yet eternally the same, a traveller without end. Have you ever stopped to truly observe the steam rising from a hot cup of tea, or the shimmering haze above a sun-baked road after a summer shower? You are witnessing the first, most ethereal stage of this cycle, evaporation. Here, water in its liquid form answers the sun's insistent call. Solar radiation, a relentless shower of energy, impinges upon the vast surfaces of our oceans, lakes, and rivers. These tiny hydrogen-bonded molecules, once content in their liquid embrace, begin to absorb this energy. They vibrate with increasing fervour, their delicate bonds stretching and straining until, with a burst of newfound freedom, they break away from the liquid mass and ascend into the atmosphere as an invisible gas, water vapour. It is a silent, microscopic liberation, yet its cumulative effect is colossal. Billions upon billions of water molecules lift off daily, carrying with them not just their own essence, but also the latent heat absorbed from the sun. This process isn't confined to open bodies of water. Even the moisture clinging to soil particles, the dew on a blade of grass, or the sweat on your skin contributes to this atmospheric migration. And then there is the silent, often overlooked contribution of life itself. Plants, those verdant architects of our terrestrial world, draw water from the soil through their roots. This water, laden with nutrients, travels upwards through their vascular systems, eventually reaching their leaves. Here, through tiny pores called stomata, it evaporates into the atmosphere. This process, unique to vegetation, is known as transpiration. When we speak of the total water vapour released into the atmosphere from both land and plant surfaces, we often combine these two processes into one overarching term: evapotranspiration. Consider the sheer volume of water transpired by a sprawling rainforest, its canopy exhaling vast, humid breaths into the air, contributing significantly to regional and global weather patterns. It is a profound collaboration between the sun, the land, and life itself, orchestrating the initial ascent of water back to the sky. As these liberated water vapour molecules rise higher into the atmosphere, they encounter a different reality. The air grows cooler. This cooling causes the water vapour to lose energy. The frantic, energetic dance of the gaseous molecules slows, and they begin to draw closer together, their attraction reasserting itself. This is where the magic of condensation truly unfolds, transforming the invisible into the visible. But water vapour, left to its own devices, is often reluctant to form droplets spontaneously. It needs a scaffold, a tiny nucleus around which to coalesce. Enter the unsung heroes of condensation nuclei. These are microscopic particles suspended in the atmosphere, specks of dust from deserts, pollen grains from flowers, sea salt crystals whipped up by ocean winds, even soot from fires. Each of these tiny particles acts as a magnet, a miniature anchor for the cooling water vapour molecules. As water vapour molecules cling to these nuclei, they release their latent heat back into the atmosphere and begin to transition from gas back into a liquid state, forming infinitesimally small water droplets, or, if the temperature is low enough, ice crystals. Multiply these invisible nuclei by billions, and you begin to understand how clouds are born. A cloud, in essence, is a vast ethereal congregation of these microscopic water droplets or ice crystals suspended in the air. From the wispy cirrus streaks high above to the towering majestic cumulonimbus, clouds are the visible manifestations of condensation, the skies holding tanks, patiently awaiting their next command. They are the atmospheric canvases upon which light and shadow play, forever reminding us of water's continuous journey. As these cloud droplets or ice crystals continue to grow, colliding and merging with others, they eventually reach a critical mass. They become too heavy to remain suspended by the air currents. At this point, gravity, that unwavering force, reclaims its due, pulling them back towards Earth's surface. This descent of water from the atmosphere in any form is known as precipitation. Precipitation manifests in a wondrous variety of ways, each influenced by atmospheric temperature and conditions. We are most familiar with rain, where liquid water droplets fall through temperatures above freezing. But when temperatures are consistently below freezing throughout the cloud and the air column below, precipitation falls as shimmering snow, each flake a unique six-sided masterpiece of frozen water. If snow melts as it falls through a warm layer of air, then refreezes into tiny ice pellets before reaching the ground, we experience sleet. And in the tumultuous, violent updrafts of powerful thunderstorms, water droplets are repeatedly carried aloft, freeze, collect more supercooled water, and fall back down, growing into layered balls of ice before finally succumbing to gravity as hail. Each form of precipitation represents water's return, a celestial delivery service replenishing the planet's vital stores. Once precipitation reaches the Earth's surface, its journey takes on new directions, dictated by the landscape, geology, and vegetation. Some of this water immediately begins to flow over the land as surface runoff. This is the water you see coursing down streets, collecting in ditches and eventually joining smaller streams that merge into larger rivers. These rivers, like the planet's arteries, carry the water inexorably towards the oceans, completing a crucial segment of the cycle. The rate and volume of runoff are influenced by many factors: the steepness of the terrain, the type of soil, the amount of vegetation, which helps absorb and slow water, and the presence of impervious surfaces like roads and buildings, which accelerate runoff. But not all water flows over the surface. A significant portion embarks on a subterranean adventure, seeping into the ground through a process called infiltration. The soil, like a vast sponge, absorbs this water. Some of it remains in the upper layers, providing essential moisture for plants. This soil moisture is a critical component of terrestrial ecosystems, sustaining forests, grasslands, and agricultural crops. Other water continues its downward journey, moving through the soil and rock layers in a process known as percolation. This water eventually reaches the saturated zone beneath the surface, where all the pores and cracks in the rock are completely filled with water. This is our groundwater, a hidden reservoir, often flowing slowly through geological formations called aquifers. Groundwater can remain underground for days, months, years, or even millennia, slowly migrating until it emerges as springs, feeds into rivers and lakes, or is drawn up by wells. It is a vast, unseen world, holding more fresh water than all the lakes and rivers combined. And so, the journey continues. Water is temporarily held in various storage points across the globe. The colossal ice sheets and glaciers at the poles and on high mountains, the vast expanse of the oceans, the numerous lakes and rivers, the moisture in the soil, the deep reserves of groundwater, and even within the very cells of living organisms, including ourselves. Each drop of water you drink has likely been part of an ancient ocean, a prehistoric cloud, or perhaps even flowed through the veins of a dinosaur. It is a testament to the fact that the water on Earth today, is essentially the same water that has been here for billions of years, constantly recycled, constantly transformed. This intricate, interconnected dance of evaporation, condensation, precipitation, runoff, infiltration, and storage forms the ceaseless engine of the hydrological cycle. It is more than just a scientific concept. It is the very essence of planetary life support. It regulates Earth's climate by distributing heat, sculpts our landscapes through erosion and deposition, and, most profoundly, provides the continuous supply of fresh water that sustains every form of life. Without this dynamic cycle, our planet would be a barren, lifeless rock. We witness then, not a static entity, but an eternal traveller, a shapeshifter par excellence. Water, the cosmic architect, continues its work, weaving the fabric of our world with every drop, every cloud, every river. And as we begin to truly appreciate the scale and complexity of this fundamental cycle, we also begin to grasp the immense responsibility we bear towards this most precious and ancient of resources. How do we, as a species, interact with this profound planetary rhythm? And what are the consequences of our engagement? These are the questions that will guide our further exploration into the depths of hydrology. We have journeyed through the cosmic birth of water, witnessed its arrival on our nascent planet, and marvelled at the ceaseless, intricate dance of its global cycle. We have seen how evaporation lifts it skyward, how condensation gathers it into clouds, and how precipitation returns it to Earth, a continuous, ancient rhythm that sculpts our landscapes and breathes life into every corner of our world. But what happens when the profound silent rhythm of this planetary pulse encounters the clamour and ambition of humanity? How do we, with our burgeoning cities and ever-growing needs, interact with this fundamental force, and what consequences ripple from our touch? As we stand on the precipice of this question, we begin to understand that the story of water is no longer just a cosmic ballet or an ecological symphony. It becomes a human drama, replete with challenges, ingenuity, and profound responsibility. For you and I and every living thing are not merely observers of the hydrological cycle, but active participants, shaping its flow and being shaped by its presence or absence. Consider for a moment the sheer scale of our dependency. Every sip you take, every meal you savour, every garment you wear, every device that powers your world, each is imbued with the silent, often invisible presence of water. Agriculture, the very bedrock of civilization, consumes the largest share, drawing vast quantities from rivers and aquifers to nourish our crops. We divert mighty rivers, channeling their ancient paths into sprawling irrigation networks that transform arid lands into fertile fields. We build immense reservoirs, crafting artificial lakes that hold back the power of nature, ensuring a steady supply for our burgeoning populations and generating the electricity that lights our homes. Industry, too, is a thirsty giant using water for cooling, for manufacturing, for cleaning, for processing. And then there is our daily domestic life, the refreshing shower, the clean dishes, the flush toilet, each a testament to the convenience and health that readily available, clean water affords us. Yet this profound dependency often comes at a cost. Our interaction with water, while essential for our survival and progress, frequently disrupts the delicate balance of the natural cycle. When we dam a river, we alter its flow, impacting the ecosystems downstream and the sediment transport that nourishes floodplains and deltas. When we pump groundwater faster than it can be replenished, we deplete ancient aquifers, causing land subsidence and threatening future supplies. When we pave over vast expanses of land for our cities, we reduce the Earth's natural capacity for infiltration, increasing surface runoff and diminishing the recharge of those vital underground reservoirs. We are in essence not just using water, but actively reshaping its journey, sometimes with unforeseen and far-reaching consequences. This brings us to one of the most pressing challenges of our era: water scarcity. Have you ever considered what water scarcity truly means? It's more than just a lack of rainfall. It's a complex interplay of factors that limit the availability of accessible clean water for all. While our planet is indeed a quote 8, with oceans covering over 70% of its surface, the vast majority of this is salt water, unusable without costly and energy-intensive treatment. Fresh water, the lifeblood of terrestrial ecosystems and human societies, constitutes a mere 2.5% of the total, with most of that locked away in glaciers and ice caps. The easily accessible liquid fresh water in rivers, lakes, and shallow groundwater makes up less than 1% of all water on Earth. And yet, our demands on this precious resource continue to escalate. Global population growth means more mouths to feed, more industries to power, more cities to sustain. Changing dietary habits, particularly a shift towards more water-intensive foods like meat, further strain agricultural demands. Climate change, the silent orchestrator of global shifts, exacerbates the problem, altering precipitation patterns, intensifying droughts in some regions, and increasing the frequency of floods in others. As temperatures rise, glaciers, the sequoia of many regions, melt at an accelerated pace, providing a temporary surge of water followed by a long-term decline. Evaporation rates increase, drying out soils and shrinking lakes. The very rhythm of the hydrological cycle, which we explored in the previous chapter, is being thrown off balance, creating unpredictable and often devastating conditions. Beyond the challenge of sheer quantity lies the equally critical issue of water quality. What good is abundant water if it is unfit for consumption or harmful to life? Here, our human footprint becomes starkly visible. Industrial processes often discharge a cocktail of heavy metals, toxic chemicals, and thermal pollution into our waterways, poisoning aquatic life and rendering water unsafe for human use. Agriculture, while feeding us, can also be a significant source of pollution, with runoff carrying pesticides, herbicides, and excess fertilizers into rivers and lakes. This influx of nutrients, particularly nitrogen and phosphorus, can lead to eutrophication, a process where excessive algal growth chokes out other aquatic life, creating, quote, 10, quote, devoid of oxygen. Our cities too contribute their share. Untreated or inadequately treated sewage, pharmaceuticals, microplastics, and countless other contaminants find their way into the water system. The paradox of water as the quote 11 is laid bare here. Its remarkable ability to dissolve and carry substances, which makes it so vital for life's processes, also makes it incredibly vulnerable to pollution. It becomes a carrier, transporting our waste and our negligence across vast distances, impacting communities far downstream and ecosystems seemingly untouched by the source of contamination. The intricate web of life, from the smallest microorganism to the largest whale, relies on the purity of this fundamental compound, and when that purity is compromised, the entire web suffers. So, what then is our path forward? How do we navigate this complex relationship with the very substance that sustains us? The answers lie in a blend of innovation, policy, and a renewed reverence for water itself. We must embrace strategies that foster sustainable water management, recognizing that every drop counts and that our actions have ripple effects. Conservation is perhaps the most immediate and impactful step. This isn't just about taking shorter showers, though individual actions are crucial. It's about systemic change, fixing leaky infrastructure that can waste vast quantities of treated water, developing water-efficient technologies for homes and industries, and promoting practices that reduce overall demand. In agriculture, where the bulk of water is used, efficient irrigation techniques like drip irrigation, which delivers water directly to plant roots, and precision farming, which uses sensors to apply water only when and where it's needed, can drastically reduce consumption. Beyond reducing demand, we must also look to innovative supply solutions. Wastewater treatment is no longer just about disposing of effluent. It's about reclaiming and reusing water for non-potable purposes like irrigation, industrial cooling, and even, with advanced purification for drinking, the once discarded becomes a valuable resource. Desalination. The process of converting salt water into fresh water offers a lifeline to arid coastal regions, though it remains energy-intensive and produces brine that must be managed responsibly. Rainwater harvesting. An ancient practice is gaining renewed importance, capturing precipitation from rooftops and other surfaces for domestic or agricultural use, reducing reliance on conventional sources. And critically, we must invest in aquifer recharge projects, allowing treated wastewater or stormwater to slowly percolate back into underground reservoirs, mimicking nature's own replenishment cycle. Ultimately, the most effective approach is an integrated water resources management, IWRM, framework. This holistic philosophy recognizes that all water, surface water, groundwater, and even atmospheric water, is part of a single, interconnected system. It calls for coordinated development and management of water, land, and related resources, balancing economic and social welfare with the sustainable protection of ecosystems. It involves engaging all stakeholders, from farmers and industrialists to urban planners and environmentalists, in decision-making processes, fostering cooperation rather than competition over this shared vital resource. As we conclude this chapter, reflecting on humanity's intricate and often challenging relationship with water, a profound truth emerges. Water is not merely a commodity to be exploited or a problem to be solved. It is a fundamental partner in our existence, a testament to the elegant design of our universe. The questions we posed at the outset about our interaction with this profound planetary rhythm and its consequences lead us to a stark realization. The future of water, and thus the future of life as we know it, rests squarely in our hands. The journey of water, from the hearts of ancient stars to the depths of our oceans, from the vapor in the sky to the stream in your backyard, is an unbroken narrative. It is a story of resilience, transformation, and enduring vitality. And now, you and I, we are part of that story. What role will we choose to play in its unfolding chapters? Will we be stewards, guardians, innovators, or will we continue to strain its delicate balance? The answer, like the flow of a river, is ever moving, ever changing, and ultimately ours to write. The Dreamy Academy invites you to ponder this as we prepare to dive deeper into the specific realms of surface water and groundwater, exploring the intricate details of their movement, their measurement, and their management. Like the video if this journey has sparked your curiosity, and subscribe to continue this shared exploration of Earth's most precious liquid. The adventure continues. Our journey through water's cosmic origins and planetary dance has revealed its profound power, its intricate cycles, and the ever-growing imprint of humanity upon its delicate balance. We've seen how our reliance on water for sustenance, industry, and the very fabric of our societies often leads to scarcity and pollution, transforming this life-giver into a source of profound challenge. But what happens after the clouds weep their precipitation onto the land? How does water then move across and beneath our world, and how do we, as its most demanding inhabitants, manage these vital pathways? Today, we turn our gaze to the immediate aftermath of the sky's generosity, the realms of surface water, and the hidden world of groundwater. These are the reservoirs, the arteries, and these silent veins that tirelessly transport water, sustaining ecosystems and civilizations alike. They are also the arenas where our management choices cast the longest shadows. Consider for a moment, or the sheer vibrancy of surface water. It is the water we see, the water we touch, the water that defines so much of our terrestrial experience. The rushing river, carving canyons through ancient rock, the placid lake, mirroring the sky and cradling a universe of life, the sprawling wetland, a symphony of reeds and calls. These are not merely scenic backdrops, they are the planet's exposed circulatory system, vibrant with life and ceaselessly at work. Rivers in particular are the very pulse of the land. Born from the convergence of countless trickles, rivulets and springs, they gather the runoff from vast watersheds or catchments, funneling it towards larger bodies of water, eventually returning to the sea. Have you ever stood by a river and felt its relentless energy? That energy is not just a force of nature. It is a fundamental geological agent. Rivers sculpt landscapes with an artistry that spans millennia, eroding mountains, depositing fertile sediments in floodplains, and shaping the very topography of our continents. They are conduits of nutrients, transport pathways for organisms, and historical cradles for human settlement. Think of the Nile, the Amazon, the Mississippi. Their stories are inextricably woven with the rise and fall of civilizations. Lakes, on the other hand, act as the land's natural reservoirs, collecting water in depressions formed by glacial scour, volcanic activity, or tectonic shifts. They offer a stable habitat for an incredible diversity of aquatic life, moderating local climates and providing essential resources, but their stillness, while beautiful, also makes them vulnerable. The pollutants we discussed in Chapter 4, agricultural runoff, industrial discharge, urban waste, often find their way into these basins, accumulating and concentrating. We witness the consequences in phenomena like eutrophication, where excessive nutrients lead to algal blooms that choke out other life, turning vibrant ecosystems into stagnant, oxygen-depleted zones. And then there are the wetlands, marshes, swamps, bogs, and fens. Often misunderstood and historically drained for development, these ecosystems are now recognized as ecological superheroes. They are nature's sponges, absorbing floodwaters and slowly releasing them, thus mitigating both floods and droughts. They are nature's kidneys, filtering pollutants and improving water quality. They are biodiversity hotspots, supporting an unparalleled array of plant and animal species, and increasingly we understand their critical role as carbon sinks, helping to regulate our planet's climate. To lose a wetland is to lose a multifaceted natural service that we can scarcely afford to replace. Managing surface water, you see, is a monumental task, fraught with challenges. We construct immense dams and reservoirs to harness rivers for hydropower, irrigate vast agricultural lands, and provide drinking water for burgeoning cities. These engineering marvels have undoubtedly fueled progress, yet they come with profound trade-offs. They alter natural flow regimes, disrupt fish migration, trap sediment that would otherwise replenish downstream deltas, and often displace communities. The competition for surface water, especially in arid regions, ignites geopolitical tensions and complex legal battles, underscoring the vital yet finite nature of this resource. And with climate change intensifying, we face more extreme floods and prolonged droughts, demanding ever more sophisticated and adaptive management strategies. But what of the water that doesn't flow across the surface? What of the silent, unseen majority, often forgotten yet profoundly essential? This brings us to the realm of groundwater. Imagine, if you will, the Earth's crust as a vast, porous sponge. When rain falls or snow melts, a portion of that water doesn't become surface runoff. Instead, it begins a slow, deliberate journey downwards, pulled by gravity through the soil and rock. This process is called infiltration. And as the water continues its descent through the unsaturated zone, the undimnvados zone, where air still occupies some pore spaces, it eventually reaches a point where all the pore spaces in the rock or sediment are completely filled with water. This is the saturated zone, and the upper boundary of this zone is what we call the water table. The geological formations that can store and transmit significant quantities of groundwater are known as aquifers. These subterranean reservoirs are incredibly diverse, ranging from vast unconsolidated sand and gravel deposits to fractured bedrock. Some aquifers are unconfined, meaning their upper boundary is simply the water table, directly connected to the surface. Others are confined, sandwiched between layers of impermeable rock or clay under pressure. The sheer volume of water stored in aquifers far surpasses all the surface water on Earth, making it humanity's largest readily available freshwater resource. The movement of groundwater, while often imperceptible to us, is a continuous, albeit slow, process. It flows from areas of higher pressure and elevation to areas of lower pressure and elevation, often discharging into rivers, lakes, or oceans, or emerging as springs. The speed and direction of this flow are governed by two key properties of the aquifer material: porosity and permeability. Porosity refers to the amount of empty space within the rock or sediment. The more pores, the more water it can hold. Permeability describes how easily water can flow through those interconnected pores. A highly porous material might not be very permeable if its pores aren't well connected, like clay. Conversely, a material like coarse sand or gravel is both porous and highly permeable, allowing water to move relatively freely. For centuries, humanity has tapped into these hidden reserves, digging wells to access the water table. Today, with advanced drilling technology, we can reach deeper, more extensive aquifers. Groundwater provides drinking water for billions, irrigates a significant portion of global agriculture, and supports countless industries. Its natural filtration through layers of soil and rock often makes it cleaner than surface water, requiring less treatment. Yet, this vital resource, precisely because it is hidden, faces its own unique and often more insidious threats. The most immediate challenge is over-extraction. When we pump water out of an aquifer faster than it can be naturally replenished, a process known as recharge, the water table drops. This leads to a phenomenon called a cone of depression around the well, and on a larger scale can cause widespread aquifer depletion. The consequences are dire. Wells go dry, pumping costs soar, and in coastal areas, the lowering of freshwater pressure allows heavier salt water to intrude, rendering the aquifer unusable, a process known as saltwater intrusion. Perhaps most dramatically, the removal of water from the pore spaces can cause the overlying land to compact and sink, a phenomenon known as land subsidence, which can damage infrastructure and permanently reduce the aquifer's storage capacity. Groundwater is also incredibly vulnerable to pollution, and here its slow movement becomes a disadvantage. Contaminants from leaking landfills, septic systems, industrial spills, and agricultural pesticides and fertilizers can slowly seep into aquifers. Once polluted, groundwater is exceptionally difficult, if not impossible, to remediate. Its slow flow means pollutants persist for decades, even centuries, spreading silently and insidiously, a legacy of contamination that can haunt future generations. As we stand at this juncture, observing both the visible dance of surface water and the hidden journey of groundwater, a critical truth emerges. These are not separate entities. They are profoundly interconnected, two facets of a single, integrated hydrological system. Rivers are often fed by groundwater discharge, base flow, especially during dry periods. Lakes and wetlands are frequently expressions of the water table at the surface. Pumping groundwater can reduce streamflow. Polluting surface water can recharge and contaminate aquifers. Therefore, any attempt to manage one without considering the other is not just incomplete, it is fundamentally flawed. The future of our water security, and indeed the well-being of the planet, hinges upon our ability to understand and manage this intricate, interconnected system as a whole. It demands an approach that transcends traditional boundaries, that embraces the complexity of the hydrological continuum, and that recognizes our profound responsibility to both the visible and invisible waters that sustain us all. The challenge is immense, but so too is the potential for innovative, integrated solutions. This is the urgent call to which we must now respond. The profound interconnectedness of surface and groundwater, a truth we explored in our last shared contemplation, leaves us with a lingering question, doesn't it? How do we, as stewards of this planet, truly grasp the intricate symphony of water, to manage it not just for today, but for all the tomorrows yet to unfold? The mystery of humanity's choices hangs heavy, a challenge whispered across the ages. To navigate this challenge, to make informed choices, we must first understand. We must learn to listen to the whispers of the water itself, to decode its movements, its ebb and flow, its hidden reservoirs. This is where the meticulous art and science of hydrology truly come into their own. We move beyond simply observing the grand hydrological cycle. Now we seek to quantify it, to measure its pulse, to understand its delicate balance with precision. Imagine, if you will, any segment of our planet, a vast ocean basin, a winding river catchment, a solitary lake, or even the soil beneath your feet. Within each of these defined systems, water is constantly in motion. It arrives, it departs, and it lingers, held in temporary embrace. This fundamental principle, elegantly simple yet profoundly powerful, is encapsulated in what we call the water balance equation. It is the bedrock of hydrological understanding, a cosmic ledger keeping track of every drop. At its core, the water balance equation states that for any given system over a specific period, the total inflow of water must equal the total outflow, plus or minus any change in the amount of water stored within that system. In simpler terms, what comes in minus what goes out is what's left or what's been lost. We write it as, consider this not as a dry formula, but as a living, breathing truth that governs every drop of water on Earth. This equation allows us to quantify the dynamics of water, to understand if a region is gaining or losing water, if a river is swelling or receding, if an aquifer is replenishing or depleting. It's the key to unlocking the secrets of water availability and vulnerability, a lens through which we can perceive the health of our planet's most vital resource. But how do we measure these elusive components? How do we quantify the invisible currents, the atmospheric rivers, the subterranean flows? This endeavour takes us into the realm of hydrological measurements, a blend of age-old techniques and cutting-edge technology. Let us begin with inflow, most often dominated by precipitation. Have you ever watched the rain fall, wondering about its volume, its intensity? We measure this crucial input with rain gauges, simple cylinders collecting the liquid gift from the sky. For a broader view, we employ radar, which bounces signals off raindrops to estimate rainfall over vast areas, and increasingly satellites, observing cloud formations and precipitation patterns from orbit. These tools allow us to map the distribution of rainfall, to understand its variability across landscapes and through seasons, revealing the uneven generosity of the atmosphere. Yet even with these advancements, the sheer spatial and temporal variability of precipitation remains a significant challenge, a constant reminder of nature's intricate, unpredictable dance. Then there is outflow, the ways water departs our chosen system. One of the most significant forms of outflow, particularly from land surfaces and water bodies, is evaporation. And transpiration, often combined and referred to as evapotranspiration. This is the great upward journey, where liquid water transforms into vapour and ascends into the atmosphere. Measuring evaporation is far more complex than catching rain. We use evaporation pans, open containers of water whose diminishing levels give us a proxy. More sophisticated methods involve eddy covariance towers, which measure the turbulent exchange of water vapour directly above ecosystems, or the energy balance approach, calculating how much energy is available to drive the phase change. For transpiration, the exhalation of water vapour by plants, we often rely on plant physiological measurements or remote sensing techniques that infer plant health and activity from satellite imagery. This unseen exodus of water driven by the sun's energy is a critical component of the water balance, often accounting for a substantial portion of a region's water budget. Another major outflow, particularly for land-based systems like watersheds, is streamflow or runoff. This is the visible journey of water across the land surface and through river channels, eventually reaching lakes, oceans, or other downstream systems. We measure streamflow at gauging stations, where instruments continuously monitor water levels, stage, and correlate them with measured flow velocities to calculate discharge, the volume of water passing a point per unit of time. Imagine a river, its powerful current carrying the story of the upstream landscape. Gauging stations are its careful scribes, recording its daily narrative. The resulting data allows us to construct a hydrograph, a graph showing streamflow over time, revealing the river's response to rainfall events, the melt of snow, and the rhythm of the seasons. These hydrographs are vital for flood forecasting, drought monitoring, and water resource allocation. And what of the hidden outflows and inflows, the subterranean currents of groundwater? As we discussed, groundwater flows are notoriously difficult to measure directly. We rely on networks of observation wells, equipped with piezometers, to monitor groundwater levels and infer flow directions and rates. Groundwater models, complex mathematical representations of the subsurface, are also indispensable tools, helping us simulate how water moves through aquifers, responds to pumping, and interacts with surface water bodies. These models, fed by geological data and observed water levels, allow us to peer into the invisible, to understand the slow, deliberate journey of water beneath our feet. Finally, we must account for the change in storage. Water doesn't just flow, it also rests, temporarily stored in various compartments. These include the water held in lakes and reservoirs, the moisture clinging to soil particles, the vast reserves within aquifers, the snow and ice locked in mountain ranges, and even the water held within the biomass of plants. Monitoring changes in these storage components is crucial. For lakes and reservoirs, we measure water levels and volumes directly. Soil moisture can be measured with sensors embedded in the ground or estimated from satellite data. Changes in groundwater storage are inferred from monitoring well networks and satellite gravimetry, like NASA's GRACE mission, which measures subtle changes in Earth's gravitational field caused by shifts in water mass. Snowpack is measured with snow courses and automated sensors. Tracking these changes allows us to understand the resilience of a water system, its capacity to buffer against periods of drought or absorb excess during floods. Why do we dedicate such effort, such ingenuity to these measurements? Why do we strive to balance this cosmic ledger? Because this data, these carefully collected numbers, are the very language of water's health. They inform our decisions, guide our policies, and illuminate the path towards sustainable water management. Without this quantitative understanding, our efforts would be blind, our interventions mere guesses. Imagine trying to manage a household budget without knowing your income or expenses. It would be chaos. The same applies to our planet's water budget. Hydrological data allows us to forecast floods and droughts. Predicting extreme events helps us prepare and mitigate their devastating impacts. Allocate water resources fairly. Understanding water availability is critical for agriculture, industry, and domestic use, especially in regions facing scarcity. Design infrastructure. Dams, irrigation systems, and water treatment plants are built based on hydrological data. Protect ecosystems. Monitoring stream flow and groundwater levels helps ensure adequate water for wetlands, rivers, and the life they sustain. assess the impacts of climate change. By tracking long-term trends in precipitation, evaporation, and storage, we can understand how our planet's water cycle is responding to a changing climate. Of course, the task is not without its challenges. The sheer scale and complexity of the Earth's hydrological system mean that perfect measurement is often an elusive ideal. Spatial variability, temporal dynamics, remote and inaccessible regions, and the inherent limitations of instruments all contribute to uncertainties. Furthermore, the very act of measurement can be impacted by the changes we are trying to track, creating a dynamic feedback loop. Yet, despite these hurdles, the field of hydrology continues to evolve. Advancements in remote sensing, geographic information systems, GIS, high-performance computing, and increasingly artificial intelligence and machine learning are revolutionizing our ability to collect, process, and interpret hydrological data. We are moving towards more integrated models, capable of simulating the entire hydrological cycle across vast scales, from the atmosphere to the deep subsurface. So, as we stand at this juncture, contemplating the future of water, the unresolved mystery from our last chapter begins to take on a new dimension. It is no longer just about if we will manage water sustainably, but how we will apply this growing body of knowledge. We have the tools, the equations, the measurements, and the ever-advancing technology to decode the language of water. The question now is whether we will listen intently, understand deeply, and act wisely. The water balance equation, seemingly simple, is a profound call to stewardship, urging us to become conscious participants in the cosmic dance of water, not just observers. It asks us to balance the ledger, not just for our own generation, but for the countless generations that will follow, who will inherit the consequences of our choices today. We have journeyed together, exploring the very essence of water, from its cosmic birth to its intricate dance within Earth's living systems. We have delved into the tireless hydrological cycle, examined the profound challenges of its management, and, in our last shared moment, embraced the quantitative language of its balance. We learned to measure, to observe, to quantify the ceaseless flow and storage of this vital fluid. But what comes next, you might ask, after we have gathered all these precious data points, after we have meticulously charted the inflows, outflows, and changes in storage? Is it merely an exercise in documentation, a grand accounting of nature's ledger? No, dear learner, it is far more. For the true power of understanding lies not just in describing what is, but in envisioning what will be. It is in the courageous leap from observation to prediction, from measurement to foresight. This is where the profound art and science of hydrological modelling and forecasting truly begin, a quest to anticipate water's next move, to read the whispers of tomorrow in the currents of today. Imagine, if you will, standing at the precipice of a vast watershed, the sky darkening with an impending storm. You know the land, the rivers, the soil. But how much rain will fall? How quickly will the rivers swell? Which towns will be spared, and which will face the rising tide? These are not questions for simple guesswork. They demand a deeper, more structured form of intuition, a system capable of synthesizing countless variables into a coherent narrative of the future. This system is the hydrological model. At its heart, a hydrological model is a simplified representation of a real-world water system. It's a conceptual framework, often expressed through mathematical equations, designed to simulate the processes of the hydrological cycle. Think of it as a meticulously crafted digital twin of a river basin, an aquifer, or even an entire continent, where we can test hypotheses, explore scenarios, and, most critically, predict outcomes. We feed these models information: the pulse of precipitation, the breadth of evapotranspiration, the texture of the land, the porosity of the soil. And in return, they offer us a glimpse into the future of water. There are many ways to build such a digital twin, each suited to different questions and scales. We might begin with conceptual models, which, as their name suggests, are built upon our understanding of physical processes, but often simplify them into, quote, 12 parameters. Picture a series of interconnected reservoirs, each representing a component of the hydrological cycle: a soil moisture store, a groundwater aquifer, a river channel. Rainfall fills the soil store, which then overflows into the river or percolates down to the groundwater. These models are elegant in their simplicity, often requiring fewer data inputs and computational power, making them powerful tools for rainfall runoff prediction in smaller basins. They capture the essence of the system without getting bogged down in every microscopic detail, much like an impressionist painting captures the mood of a landscape without depicting every leaf. Then we ascend to the realm of physically based models. These are the grand cathedrals of hydrological simulation, attempting to represent the underlying physical laws of water movement with far greater detail. Imagine dividing a watershed into thousands, even millions of tiny cells, each with its own unique characteristics of slope, soil type, and vegetation. Within each cell, and between them, we apply the equations of fluid dynamics, energy balance, and mass transfer. These models can simulate water flow across the surface, through the soil, and into the groundwater, often in 3 dimensions. They demand vast amounts of data: detailed topography, land cover maps, soil hydraulic properties, and immense computational power. But in return, they offer a spatially distributed understanding of water's journey, allowing us to pinpoint areas vulnerable to erosion, predict specific flood inundation zones, or trace the path of a contaminant through an aquifer. They are like a master architect's blueprint, detailing every pipe and beam of a complex structure. And finally, in an age brimming with data, we encounter data-driven or empirical models. These models often operate without a deep explicit understanding of the physical processes. Instead, they seek patterns and relationships directly from observed data. Think of powerful statistical techniques or, more recently, machine learning algorithms. We feed them historical records of rainfall and streamflow, for instance, and they learn to predict future streamflow based on new rainfall data, identifying complex nonlinear relationships that might elude our direct physical formulation. They are like a seasoned diviner who, by observing the myriad signs of the natural world over countless seasons, learns to predict the harvest without necessarily understanding the specific biochemical pathways of plant growth. While powerful, their predictions are only as good as the data they learn from, and they may struggle when faced with conditions outside their past experience. Regardless of their underlying philosophy, all hydrological models demand inputs and yield outputs. What do we feed these digital brains? We provide the atmospheric forces, the cadence of a precipitation, from rain gauges and radar, the sun's energy for evaporation, the wind's sweep, the air's humidity. We describe the land's surface, its topography, the type of vegetation covering it, the year soil characteristic that dictate infiltration and storage. For groundwater models, we map the geological layers, the aquifer properties like porosity and permeability. And what do they give us in return? A treasure trove of predictions. They can generate hydrographs showing anticipated river flows, identifying peak flood levels and timings. They can map out flood inundation zones, revealing which areas will be submerged. They can forecast soil moisture deficits, signaling the onset of drought. They can predict groundwater levels and even the movement of pollutants through aquifers. For those managing vast water resources, models can optimize reservoir releases, balance competing demands for irrigation and hydropower, and ensure environmental flows for delicate ecosystems. Yet, a model, no matter how sophisticated, is merely a tool. Its reliability hinges on two critical processes: calibration and validation. Imagine you've built a magnificent clockwork device designed to predict the tides. Before you trust it, you must first calibrate it. You adjust its gears and springs, comparing its predictions to known historical tide data, fine-tuning its mechanisms until it accurately reproduces the past. This is calibration, adjusting the model's internal parameters, like soil infiltration rates or river roughness coefficients, until its simulated outputs closely match observed data. Once calibrated, you then validate it. You test your clockwork against a different set of historical tide data it has never seen before. If it performs well on this new independent data set, then you gain confidence that your model can indeed predict the future. Without rigorous calibration and validation, a model is little more than an educated guess. With them, it becomes a powerful instrument of foresight. The applications of this predictive power are vast and profoundly impactful. In the face of nature's formidable forces, hydrological models offer us a shield and a guide. Consider flood forecasting and warning systems. In regions prone to inundation, models are continuously fed real-time precipitation data. They simulate the rapid rise of rivers, calculate the travel time of floodwaters, and predict the extent of their spread. This allows authorities precious hours, sometimes even days, to issue warnings, evacuate communities, and deploy emergency services, transforming potential catastrophe into managed risk. Lives are saved, property protected, economies shielded from the full brunt of nature's fury. Conversely, in the slow creeping grip of drought, models become indispensable for monitoring and management. They track soil moisture levels, groundwater reserves, and reservoir storage, identifying areas under stress long before the crisis becomes acute. This foresight enables water managers to implement conservation measures, allocate scarce resources judiciously, and plan for alternative supplies, mitigating the devastating impacts on agriculture, ecosystems, and human populations. Beyond immediate crises, hydrological models are cornerstones of water resources planning and management. When we design new dams, reservoirs, or irrigation schemes, models help us understand the long-term water availability, the potential impacts on downstream ecosystems, and the optimal operating rules for these massive infrastructures. They help us answer complex questions, How much water can a growing city sustainably draw from its sources? What are the environmental flows necessary to sustain a river's health? How will changing land use, like deforestation or urbanization, alter the water balance of a basin? Furthermore, models are vital for environmental impact assessments. Before a new development is approved, models can predict how it will affect local hydrology, changes in runoff, infiltration, groundwater recharge, or even the transport of potential pollutants. This allows for informed decision-making and the implementation of mitigation strategies to protect our precious natural environments. And in our era of rapid global change, hydrological models are frontline tools for understanding climate change impacts. By feeding them projections of future temperature and precipitation patterns, we can simulate how water resources might shift, where droughts will intensify, where floods will become more frequent, how snowpack and glacier melt will change, profoundly altering water availability for billions. This allows us to plan for adaptation, to build resilience into our water systems, and to protect vulnerable communities. Yet, for all their power and sophistication, hydrological models are not infallible crystal balls. They come with inherent challenges and limitations. They are simplifications of incredibly complex natural systems, and every simplification introduces uncertainty. The input data we feed them, while meticulously collected, always contains some degree of error or uncertainty. The very equations we use to represent physical processes are approximations. Computational demands can be immense, requiring powerful supercomputers for high-resolution, physically based simulations. And perhaps most critically, models require expert interpretation. A model's output is not a definitive truth, but rather a probable scenario, a guide to understanding. It demands critical thinking, an awareness of its limitations, and a deep hydrological understanding from the person wielding it. As we look to the horizon, the future of hydrological modeling is breathtaking. We are witnessing the integration of increasingly sophisticated remote sensing data, satellite imagery providing unparalleled spatial and temporal coverage of precipitation, land cover, and water levels. Artificial intelligence and machine learning are revolutionizing data-driven approaches, uncovering hidden patterns and making predictions with unprecedented accuracy. Real-time modeling systems, fed by vast networks of sensors and the Internet of Things, are bringing us closer to instantaneous dynamic forecasts. Even citizen science is contributing, with individuals collecting data that can feed and validate local models. So, dear explorer, as we conclude this chapter on the predictive power of hydrology, we return to the question that lingered at the end of our last journey. Will we use this growing scientific understanding wisely? Hydrological models offer us a profound capability, the ability to peer into the future of water, to anticipate its movements, to understand the consequences of our actions. They empower us to make informed decisions, to design sustainable solutions, and to protect this most precious resource. They are not magic, but rather the distilled wisdom of countless observations and scientific principles, brought to life through mathematics and computation. They are a testament to our ingenuity, a bridge between our current understanding and our future responsibilities. The power to foresee is a sacred trust. It is up to us, armed with these remarkable tools, to ensure that the whispers of tomorrow's water tell a story of balance, resilience, and flourishing life. For in understanding water's future, we ultimately secure our own. Are you ready to embrace this profound power, this vital responsibility? We continue to build this future together. We have journeyed together, tracing water's cosmic lineage, witnessing its tireless dance across our blue marble, and dissecting the intricate mechanisms of its endless cycle. We have peered into the depths of hydrological models, understanding how they translate the chaotic symphony of nature into quantifiable predictions, forecasts of floods that surge, droughts that wither, and the subtle shifts in our planet's vital pulse. These models, born of our collective ingenuity, are powerful instruments, offering us a glimpse into water's future, a map of its potential paths. But what do we do with this map? What becomes of this profound understanding, this hard-won foresight? This, dear learners, is where the journey shifts from observation and prediction to deliberate action. This is where the wisdom we have cultivated must blossom into responsible stewardship. For merely knowing is not enough. The true test of our understanding lies in how we choose to interact with this miraculous substance, how we choose to manage its delicate balance. Consider for a moment the immense responsibility that comes with such knowledge. We now understand the profound interconnectedness of every drop, every vapor, every ice crystal. We know that a decision made in one river basin can ripple through ecosystems hundreds of miles away, affecting the very groundwater that sustains communities generations removed. The challenge before us is not just technical, it is ethical, social, and deeply philosophical. It calls for an approach that transcends silos, embracing the fluidity and dynamism that water itself embodies. This is the essence of Integrated Water Resources Management, IWRM, a holistic philosophy that recognizes water not merely as a commodity, but as an integral part of the ecosystem, a finite and vulnerable resource crucial for sustaining life, development, and the environment. It asks us to view water management through a wide lens, considering all its facets: surface water and groundwater, quantity and quality, human needs and ecological health. It demands collaboration, bringing together engineers, scientists, policymakers, economists, and communities, fostering dialogues where diverse perspectives converge on common sustainable goals. Think of it as tending a vast, intricate garden. We cannot simply focus on watering one plant while ignoring the health of the soil, the needs of other species, or the changing seasons. Each element is interwoven, contributing to the vitality of the whole. Similarly, IWRM compels us to consider the entire water system: the rivers flowing, the aquifers recharging, the wetlands filtering, the forests transpiring. It urges us to protect the source, manage the demand, and treat the effluent, ensuring that water's journey continues its life-giving purpose, unimpeded and unpolluted. One of the most immediate and impactful steps we can take, individually and collectively, lies in efficiency and conservation. Have you ever truly considered the journey of the water that flows from your tap? The energy expended to treat it, pump it, and deliver it? The preciousness of each drop becomes palpable when we trace its path. In agriculture, where the vast majority of fresh water is consumed, innovations like drip irrigation, precision farming, and drought-resistant crops can drastically reduce water footprints. Industries, once notorious for their profligate use, are increasingly adopting closed-loop systems, recycling water multiple times within their processes. And in our homes, simple conscious choices, fixing leaks, shorter showers, water-efficient appliances, collectively conserve billions of gallons. It's not about deprivation, it's about respect, about valuing what is finite. It is about understanding that abundance is not an invitation to waste, but a call to cherish. But conservation alone, while critical, cannot shoulder the entire burden. Our infrastructure, the very arteries and veins of our water systems, must also evolve. For centuries, our approach has been dominated by, quote, massive dams, vast reservoirs, extensive canal networks, and intricate pipe systems designed to control and deliver water. These marvels of engineering have brought prosperity and mitigated risks, but they often come at an ecological cost, altering natural river flows, fragmenting habitats, and disrupting the very ecosystems that naturally regulate water. Now, we are learning to complement these with, quote, solutions inspired by nature itself. Imagine urban landscapes designed with permeable pavements that allow rainwater to infiltrate the ground, replenishing aquifers instead of rushing into storm drains. Envision constructed wetlands that naturally filter pollutants, creating vibrant habitats while purifying water. Think of restored floodplains that absorb excess river flow, mitigating floods while supporting biodiversity. These living systems are not just cost-effective, they are resilient, self-sustaining, and inherently beautiful, weaving human needs back into the fabric of the natural world. They represent a paradigm shift, recognizing that nature is not merely a resource to be managed, but a partner to be collaborated with. And what of the water we have used? Once considered waste, wastewater is increasingly seen as a valuable resource. Water reuse and recycling. Technologies are transforming sewage into potable water, industrial effluent into process water, and stormwater into irrigation for parks and gardens. It is a testament to our growing understanding of the hydrological cycle that we are learning to mimic nature's own purification processes, closing the loop on water's journey within our anthropogenic systems. This circular economy of water reduces our reliance on pristine freshwater sources, easing the pressure on our rivers and aquifers. Even the vast, salty expanse of the ocean, once an insurmountable barrier, is yielding its fresh water through desalination. While energy-intensive and often costly, it offers a lifeline in arid coastal regions, converting seawater into drinking water. Yet, we approach such technologies with caution, understanding their environmental footprint and viewing them as a strategic tool rather than a universal panacea. Every solution, we learn, carries its own set of considerations, its own intricate balance of benefits and impacts. At the heart of all these strategies lies the profound realization that ecosystem protection is not a luxury, but a fundamental pillar of water security. Rivers are not just conduits, they are living arteries teeming with life. Wetlands are not just soggy lands, they are Earth's kidneys, filtering and purifying. Forests are not just timber, they are sponges, regulating rainfall and preventing erosion. When we protect these natural systems, we are not just preserving biodiversity, we are safeguarding the very infrastructure that provides us with clean, abundant water. We are ensuring environmental flows, the water required to sustain freshwater and estuarine ecosystems, and the human livelihoods and well-being that depend on them. It's a recognition that water's primary purpose extends far beyond human consumption. It is the lifeblood of the planet itself. Yet, even with the most sophisticated models and ingenious technologies, the ultimate success of sustainable water management hinges on the human element. Science provides the how, but policy, economics, ethics, and social equity provide the why and the who. Who has access to water? Who bears the burden of its scarcity or pollution? How do we fairly allocate a resource that knows no political boundaries? These are questions that demand dialogue, compromise, and a shared commitment to justice. This is why governance and collaboration are paramount. Water, by its very nature, transcends borders. Rivers flow through multiple nations. Aquifers lie beneath different jurisdictions. International agreements, transboundary water commissions, and local community engagement are not just bureaucratic necessities. They are expressions of a shared destiny, a collective understanding that our individual well-being is inextricably linked to the health of the entire hydrological system. It requires leadership, vision, and a willingness to transcend narrow self-interest for the greater good. And of course, the shadow of climate change looms large over all our water management efforts. We have seen how a warming planet intensifies the hydrological cycle, leading to more extreme floods and prolonged droughts, accelerating glacier melt and altering traditional precipitation patterns. Our models predict these shifts with increasing accuracy, providing us with invaluable data. But prediction must now fuel adaptation and resilience. We must design water systems that can withstand greater variability, develop early warning systems for extreme events, and foster agricultural practices that are robust against changing climates. Sustainable water management, therefore, becomes a critical component of our broader climate adaptation strategy, a shield against the unpredictable forces we have unleashed. As we conclude this chapter of our journey, we return to the fundamental mystery that has underpinned our exploration. Will humanity wisely apply its increasing scientific understanding and predictive capabilities to achieve sustainable water management? The answer, dear friends, remains unwritten. It is being forged in the decisions we make today, in the policies we enact, in the technologies we embrace, and in the values we uphold. We have moved from the cosmic origins of water to the intricate dance of its molecules, from the vastness of oceans to the invisible flow of groundwater. We have seen its power to shape planets and sustain life, and its vulnerability in the face of human impact. Now armed with knowledge, with models, and with a growing array of sustainable solutions, the choice is ours. Do we continue down a path of consumption and disruption, or do we embrace our role as stewards, honouring water's profound essence, ensuring its abundance and purity for generations to come? The answer, like water itself, is fluid. It is constantly forming, constantly moving, constantly inviting us to participate in its creation. We have the tools, we have the understanding. What will we build? What future will we sculpt for water and for ourselves? The journey, as always, continues, and its direction rests in our hands. We stand at a precipice, don't we? After journeying through the cosmic ballet of water's birth, tracing its intricate dance across our planet, and dissecting the profound challenges it faces, we arrive at a pivotal question. The last chapter left us pondering whether our burgeoning scientific understanding and sophisticated predictive models would truly translate into the wisdom needed for sustainable water management. The answer, we mused, remains as fluid and ever-changing as water itself, yet to be etched by our collective choices. But what are these choices? How do we move from the abstract principles of integrated water resources management, IWRM, to tangible actions that secure water's abundance and purity for generations to come? This is where our journey deepens, moving from understanding to implementation, from theory to the very real, often complex, work of shaping our water future. Consider the vastness of the challenge. Water, in its very essence, respects no artificial boundaries. A river that begins as a trickle in one nation flows through several others, nourishing ecosystems and communities along its path, before finally emptying into a shared ocean. Groundwater aquifers, vast subterranean reservoirs, often stretch beneath multiple states or even countries. This inherent transboundary nature of water immediately tells us that local solutions, while crucial, are rarely sufficient in isolation. This is where the power of one policy and governance steps in, a force as invisible yet as vital as the atmospheric pressure that holds our breath. We are talking about the agreements, laws, regulations, and institutions that guide how societies allocate, manage, and protect their water resources. Imagine, if you will, a global tapestry woven not just with scientific data, but with threads of diplomacy, equity, and shared responsibility. At the international level, this translates into transboundary water agreements, treaties and commissions that bring nations together to share data, coordinate management strategies, and resolve potential conflicts over shared rivers, lakes, and aquifers. Think of the Mekong River Commission, or the agreements governing the Nile, or even the complex arrangements for the Great Lakes between the US and Canada. These are not mere bureaucratic exercises, they are profound acts of collective will, acknowledging that the fate of one's water is inextricably linked to the actions of one's neighbours. They embody the spirit of IWRM, seeking to balance economic development, environmental protection, and social equity across political divides. It's a testament to our capacity for collaboration, a hopeful counterpoint to the often fragmented nature of human endeavour. Domestically, IWRM principles cascade down into national water policies, regional plans, and local ordinances. These frameworks aim to break down the traditional silos where water for agriculture, industry, energy, and urban supply were managed independently. Instead, they promote a holistic view, recognizing the interdependencies. For instance, a policy promoting efficient irrigation in agriculture might simultaneously reduce strain on urban water supplies and improve downstream water quality. A regulation protecting a wetland doesn't just preserve biodiversity, it acts as a natural flood buffer and a water filter, benefiting human communities. Yet policy is only as effective as its enforcement and the commitment of those it governs. This brings us to another critical layer of solution: technological innovation. While we have explored hydrological models as powerful predictive tools, the realm of water technology extends far beyond, offering tangible ways to augment supply, purify contaminated sources, and optimize usage. Have you considered the remarkable advancements in water treatment and purification? We've moved beyond basic filtration to sophisticated membrane technologies like reverse osmosis, capable of removing even microscopic contaminants, transforming brackish water or even wastewater into potable supplies. Imagine cities where every drop of wastewater is meticulously treated and recycled, not just for irrigation or industrial use, but for direct human consumption. This concept of a closed-loop water system, once a futuristic dream, is becoming an increasingly viable reality in water-stressed regions, challenging our perceptions of what waste truly means. And then there's raw desalination, the grand promise of converting the ocean's boundless salty embrace into fresh water. While energy-intensive and often costly, advancements in membrane technology and renewable energy integration are making it a more sustainable option for coastal communities facing severe scarcity. It's a reminder that even the most seemingly insurmountable challenges can yield to human ingenuity, though we must always weigh the environmental footprint of such large-scale interventions. Beyond creating new sources, technology empowers us to use our existing water more wisely. Smart irrigation systems, for example, utilize soil moisture sensors, weather data, and even satellite imagery to deliver precise amounts of water directly to crops, dramatically reducing agricultural waste. In urban environments, smart metering and leak detection technologies can identify and fix infrastructure vulnerabilities, preventing millions of gallons from being lost before they ever reach a tap. These innovations represent a shift from simply managing scarcity to actively creating abundance through efficiency. However, even the most brilliant policies and cutting-edge technologies will falter without the right economic instruments. And, crucially, the sustained engagement of communities and individuals. Think about the economic levers we can pull. Water pricing, for instance, when structured equitably, can incentivize conservation. If water is undervalued, treated as an infinite commodity, there is little motivation to conserve it. But when its true cost, including the environmental and social costs of extraction, treatment, and delivery, is reflected, it encourages more mindful consumption. This isn't about making water inaccessible. It's about ensuring its value is recognized and that mechanisms exist to support vulnerable populations. Innovative approaches like water markets, where rights to use water can be traded, can, if carefully designed and regulated, encourage efficient allocation and investment in water-saving technologies, allowing water to flow to its most productive uses while respecting environmental flow requirements. Yet, perhaps the most profound shift must occur within ourselves, within our communities. Education and awareness are not merely add-ons, they are the bedrock upon which all sustainable water management must be built. How can we expect individuals to conserve water if they don't understand its journey, its interconnectedness, or the fragility of its supply? How can communities advocate for better policies if they are unaware of the threats to their local rivers or aquifers? This is where initiatives like our Dreamy Academy play a role, fostering a deep appreciation and understanding of hydrology. It's about shifting cultural norms, moving from a mindset of passive consumption to one of active stewardship. It's about empowering local communities to become guardians of their watersheds, to participate in decision-making processes, and to implement grassroots conservation efforts. Imagine school programs that teach children about their local water cycle, community gardens that employ rainwater harvesting, or neighborhood groups that organize river cleanups. These seemingly small actions, multiplied across millions, coalesce into a formidable force for change, and as we look to the future, we cannot ignore the looming shadow of climate change. Previous chapters touched on its exacerbating effects, more intense droughts, more extreme floods, unpredictable rainfall patterns, and melting glaciers. Therefore, a significant part of our water management strategy must involve climate change adaptation. This means building resilience into our water systems. It might involve constructing green infrastructure, restoring wetlands, preserving floodplains, and planting urban forests, which can naturally absorb excess stormwater, recharge groundwater, and mitigate heat island effects. It means diversifying our water sources, perhaps combining surface water with groundwater, recycled wastewater, and even desalinated water, to reduce reliance on any single vulnerable supply. It means investing in robust early warning systems for floods and droughts, informed by sophisticated hydrological models that account for a changing climate. It means fostering agricultural practices that are more water efficient and climate resilient, such as drought-resistant crops and precision farming techniques. Ultimately, the journey towards sustainable water management is not a linear path to a fixed destination. It is a continuous process of learning, adapting, innovating, and collaborating. It demands a blend of scientific rigor, technological prowess, equitable policy, economic wisdom, and most importantly, a profound ethical commitment to the planet and to future generations. We've explored the wonders of water, from its atomic structure to its planetary influence. We've seen its beauty, its power, and its vulnerability. Now, we stand at the threshold of its future, a future that we are actively writing drop by precious drop. The tools are at our disposal, the knowledge is accumulating, and the urgency is undeniable. The question from Chapter 8 echoes still. Will we choose wisely? Will we rise to the challenge, guided by the very humility and awe that water itself inspires? The answer, dear learners, is not solely for hydrologists or policymakers to determine. It resides within each of us, in our daily choices, in our collective advocacy, and in our willingness to see water not just as a resource, but as the very essence of life, deserving of our utmost reverence and care. The story of water and our place within it continues to unfold, and we, together, are its authors. Like the video? Subscribe to Dreamy Academy for more explorations into the wonders of our world. We have journeyed together, haven't we? From the cosmic dust that cradled water's birth, through the intricate dance of its molecular structure, to the relentless grand ballet of the hydrological cycle. We've peered into the hidden arteries of groundwater, tracing its silent subterranean flow through ancient rock formations, feeling the slow, deliberate pulse of an unseen world beneath our feet. We've charted the pulsing veins of rivers, watching them carve canyons, nourish floodplains, and ultimately merge with the vast expanse of the oceans, each drop a testament to ceaseless movement. And we've grappled with the complex, often messy web of human interaction that shapes water's destiny, from ancient aqueducts to modern megadams, from a simple well to a sprawling desalination plant. We've learned of measurements that track its every move, from satellite imagery discerning global trends to a single sensor monitoring a local stream's health. We've explored models that predict its future, sophisticated algorithms attempting to decipher the intricate dance of climate and consumption, and we've dissected policies designed to guide its use, from local zoning laws to international treaties, each an attempt to impose order on a force both vital and capricious. We understand the vital necessity of integrated water resources management, recognizing that every component, from rainfall to wastewater, is part of a single, interconnected system. We've seen the promise of green infrastructure where nature's own designs, like wetlands and permeable pavements, offer elegant solutions. We've celebrated the power of innovation, from advanced filtration to smart irrigation, pushing the boundaries of what's possible. And we've come to appreciate the indispensable role of community engagement, acknowledging that true stewardship begins with those who live closest to the water. But as our exploration deepens, as the wealth of knowledge we've accumulated begins to truly settle within us, we find ourselves standing at the precipice of the ultimate question. It is an unresolved mystery that transcends mere scientific understanding and technical prowess, a profound query that resonates not just in our minds, but in the very core of our being. We possess the knowledge, a veritable library of facts and figures. We have the tools, from advanced analytics to cutting-edge engineering. We can even foresee many of the challenges that lie ahead, exacerbated by the relentless march of a changing climate, its shadow lengthening across our landscapes. Yet this profound question remains hanging in the air like an unanswered prayer, a silent plea echoing through time. Will humanity collectively apply this vast scientific understanding and its predictive capabilities with the wisdom and ethical commitment necessary to ensure water's abundance and purity for future generations? The weight of this question, the sheer gravity of its implications, can feel overwhelming. One might pause, take a deep breath, and wonder if we, as a species, are truly up to the task. This isn't a question that can be answered by an equation or plotted on a graph, nor can it be solved by a single technological breakthrough. It delves into the very core of our shared humanity, into the choices we make both individually and collectively every single day. What holds us back? Is it the sheer daunting complexity of the natural and engineered systems we've created, a tangle of pipes, policies, and ecosystems that seems impossible to fully grasp? Is it the competing demands of diverse interests, farmers needing water for crops, cities for drinking, industries for manufacturing, and environmentalists for ecosystems, each clamouring for their share? Or is it perhaps a more fundamental disconnect, a profound spiritual or emotional chasm that separates us from the inherent profound sacredness of water itself? We often see water primarily as a resource, a commodity to be bought and sold, a utility to be managed and delivered, and it is indeed all these things. But it is also so much more. It is life, the very solvent of our existence. It is memory, held in the ancient ice and the flowing rivers, bearing witness to epochs. It is the fundamental medium through which existence expresses itself, from the smallest cell to the grandest ocean. To reduce it to mere utility is to diminish ourselves, to forget the wonder of its presence. Consider the ethical dimensions of this stewardship, the profound responsibility that falls upon our shoulders. We speak of sustainability, a concept that inherently carries the weighty principle of intergenerational equity. It forces us to look beyond our immediate needs, beyond the next quarter, beyond the next election cycle, and into a distant future we will never personally inhabit. What legacy do we truly wish to leave for those who will follow us, generations hence, children yet unborn whose faces we cannot even imagine? Will they inherit parched lands, cracked and barren, where once fertile fields lay? Will they find poisoned rivers, their waters toxic and lifeless, their banks littered with the detritus of our consumption? Or will they instead find clean, flowing waters sustained by the foresight, the wisdom, and the ethical commitment of their ancestors? Our decisions today ripple forward through time, like stones dropped into a vast unseen pond, shaping landscapes and lives far beyond our immediate gaze. This is not merely about managing a resource, a task that can feel cold and technical. It is about tending to a birthright, a universal inheritance that belongs to all, an inheritance we hold in trust for the future. It's a profound thought, isn't it? That our actions now dictate the very quality of life for those who come after us. Then there is the equally pressing question of intragenerational equity, or justice, which demands our immediate attention. Even today, in an age of unparalleled technological advancement and global interconnectedness, billions lack consistent access to safe, clean drinking water. Their daily lives a constant struggle for this most basic necessity. Meanwhile, others consume it lavishly, often without a second thought, filling swimming pools, watering sprawling lawns in arid climates, or engaging in industries that are notoriously water-intensive. Water, the great equalizer in its fundamental presence, essential to every human life, becomes a stark divider in its accessibility, creating chasms of privilege and deprivation. How do we ensure that the burden of scarcity, a challenge intensifying with climate change, does not fall disproportionately on the most vulnerable among us? The poor, the marginalized indigenous communities. How do we balance the ever-growing needs of burgeoning cities with their thirst for development and daily life, with the demands of agriculture, which feeds us all? And how do we reconcile the requirements of industry, driving economic growth, with the fundamental sustenance of ecosystems, which provide the very air we breathe and the water we purify? These are not abstract debates confined to academic papers. They are lived realities for countless communities around the globe, where the struggle for water can ignite conflict, deepen poverty, and perpetuate cycles of injustice. One cannot simply look away from these disparities. They demand our moral engagement. And let us not forget ecological justice, a concept that asks us to expand our ethical circle beyond humanity. Water does not exist solely for human consumption, a mere input for our activities. It is the lifeblood of every ecosystem, from the smallest microbial community to the grandest rainforest. It is the patient, persistent sculptor of landscapes, carving valleys, shaping coastlines, and nurturing the very soil beneath our feet. It is the fundamental medium that allows vast forests to breathe, drawing moisture from the ground to the sky, and permits oceans to teem with an astonishing diversity of life. Rivers have a right to flow, not just as conduits for our waste or sources for our taps, but as living entities that sustain entire biomes. Wetlands have a right to filter, to act as nature's kidneys, purifying water and supporting migratory birds. Aquifers have a right to recharge, to replenish their ancient stores, ensuring the long-term health of our planet. When we divert, dam, or deplete water bodies without regard for the intricate web of life they support, when we treat them as mere resources to be exploited, we unravel the delicate fabric of our planet, often to our own long-term detriment. The health of our water systems is inextricably linked to the health of all life, including our own species. We are not separate from nature, we are an integral part of it. This complex tapestry of challenges calls not merely for more knowledge, but for wisdom, a quality distinct from and yet built upon mere factual understanding. Knowledge is the accumulation of facts, the understanding of mechanisms, the ability to predict outcomes based on data. Wisdom, however, is the discerning application of that knowledge, infused with foresight, empathy, and a deep ethical compass. It's the ability to see the interconnectedness of all things, to understand the long-term consequences of our short-term actions, and to consistently prioritize the collective good over immediate gratification. It's the courage to make difficult choices, to challenge unsustainable practices that benefit a few at the expense of many, and to embrace innovative solutions that honor both the vital needs of humanity and the imperative health of ecological systems. It requires stepping back from the immediate noise and looking at the bigger picture, even when that picture is uncomfortable. The intensifying drumbeat of climate change renders this quest for wisdom even more urgent, transforming what might once have seemed like distant concerns into immediate crises. We are witnessing dramatic shifts in precipitation patterns, with some regions experiencing unprecedented deluges and others enduring prolonged crushing droughts. We are seeing more frequent and intense extreme weather events, floods that devastate communities and droughts that parch agricultural lands, becoming the new normal. The melting of glaciers and ice caps, once seen as remote phenomena, now directly impacts the major river systems that feed billions of people. Sea level rise relentlessly threatens coastal freshwater aquifers with saltwater intrusion, contaminating vital drinking water sources. Meanwhile, rising global temperatures increase evaporation rates from reservoirs and soils, altering water demand and availability in unpredictable ways. These are not distant, abstract threats. They are here, now, amplifying every existing challenge we face in water management, turning existing tensions into outright conflicts. Our predictive models, honed over decades by dedicated scientists, show us these futures with increasing clarity, painting vivid, often alarming, pictures of what lies ahead. The question is no longer if these changes will occur, but how we will respond, and whether that response will be adequate, timely, and wise. Can we, as a global community, transcend our differences, our nationalistic tendencies, our economic rivalries, our cultural divides, and forge a collective will to act? This will require more than just governmental policies and international agreements, though these are undoubtedly crucial frameworks. It demands a fundamental shift in perception and behavior at every level of society, from the individual household to the multinational corporation. It calls for individuals to embrace conservation and efficiency in their daily lives, understanding that every drop saved contributes to the larger whole. It calls for communities to champion local water stewardship initiatives, becoming guardians of their own springs, rivers, and aquifers. It calls for businesses to adopt water-smart practices, innovating not just for profit but for planetary well-being. And it calls for nations to cooperate across borders, transforming potential conflicts over shared water resources into shared solutions, recognizing that water knows no political boundaries. This is perhaps the hardest part, overcoming human nature's resistance to collective action, yet it is utterly essential. Imagine a world where every single drop of water is valued, cherished, and protected. Imagine a future where water is treated not as an infinite given, a resource to be squandered, but as the precious, finite and sacred gift it truly is. Imagine cities that are sponges, harvesting rainwater from every rooftop and street, recharging urban aquifers. Imagine industries that operate in closed loops, recycling their process water with unparalleled efficiency, turning waste into resource. Imagine farms that irrigate with precision and minimal loss, using every drop to maximize yield without depleting local sources. And imagine ecosystems that thrive under our respectful guardianship, their rivers flowing freely, their wetlands teeming with life, their aquifers replenished. This vision is not utopian, a mere fantasy. It is achievable, grounded in the very scientific principles and technological advancements we have explored throughout our journey together. The knowledge is there, the tools are within our grasp. Remember the journey we began, tracing water back to its cosmic origins. Hydrogen forged in the hearts of ancient stars, oxygen from the fiery death of massive suns, elements flung across the universe. This ubiquitous molecule, H2O, arrived on our young planet carried by icy comets, a miraculous delivery from the cosmos. It has since been tirelessly shaping Earth, carving mountains and filling oceans, sustaining every form of life, and witnessing the entirety of our history, from the first single-celled organism to the complexity of human civilization. It is a fundamental paradox, simultaneously fragile and powerful, a single molecule yet capable of immense force, simple in its chemical composition, yet infinitely complex in its ecological roles, silent in its presence yet constantly speaking of life and change, of cycles and renewal. Now, as our time together in the Dreamy Academy draws to a close, we return to that initial sense of wonder, but with a deeper, more urgent understanding. Water is not just H2O. It is the essence of our existence, a profound connection to the universe itself, to the very fabric of time and space. Our scientific understanding has lifted the veil, revealing the intricate mechanisms of its power and presence, its vulnerabilities, and its resilience. But the ultimate test lies not in what we know, but in how we choose to wield this knowledge. Will we be wise stewards, ensuring that the miraculous journey of water continues to nourish life for all time, a legacy of abundance and purity? Or will we allow short-sightedness, apathy, and conflict to diminish this most precious of gifts, leaving a legacy of scarcity and regret? The answer, dear learner, rests with us all. It rests with you, with me, with every choice we make and every action we take, however small they may seem. The story of water, in its most crucial chapter, is still being written. What will our contribution be to this unfolding narrative? The future of water, and with it, the future of life on Earth as we know it, awaits our collective wisdom and unwavering commitment. The time for contemplation is over. The time for action is now.